Good evening, students. My name is Shashank Shekhar, and we are doing a crash course for the upcoming JEE exam on chemistry for the 45 days. We have started yesterday the chemical kinetics chapter, and we have studied about the order and molecularity and all. So today we will see the integrated and the differential law of the form of the rate law. So we have studied yesterday the rate law, which was as like this. So it was rate is equals to K into concentration of reactant raised to some power that is or equals or not equals to the stoichiometric coefficient that is according to equation. Now this x is said as the order of reaction. Order of reaction. Also, if it is a multi-component reactant and it has two reactant x and y, then in that case the order will be x plus y. So you understand this thing now, that it is just the raise of power that will be added, and the numerical which will get the value which will get will be the order of reaction. Okay, good morning, Janvi. So this is the thing about the rate law. Now we will study about two forms of the rate law. The first one is the integrated law, and the second one is the differential law. Okay, so let us start our thing. Okay. Sorry for the interruption. Okay. So before moving to the this section of chemical kinetics, we will study some of the graphs. Basically, you have to draw multiple type of graph in this chemical kinetics about for the first law, for the zero law, zero order reaction. So that for that reason, first we will deal with the graphs. So the first graph I are seeing here is a of a straight line. So the equation of a straight line we know very clearly. It is given as y is equals to mx plus c, where y is the and x are the intercepts. Okay, sorry, the axis, and c is the intercept, and m is the slope of the given straight line. So the slope can be either positive. So in this case it is positive, or it can be negative. And this is the intercept that we have, that is equals to c. So this value will be equals to c, and for positive intercept this value will be equals to c. So this is the very for firstmost equation. This will be used to and fro in every say order of reaction. The second graph that we have here is of y is equals to ex. That is exponential graph, so it is rising like this. Okay. Similarly, if we have a y is equals to e minus x, that is y is equals to e to the power minus x, then in that case the graph will look like this. It will just be opposite of this, which will look like this. Okay. So these are the graph of y is equals to x. So this will be also used. So I will make you learn some of the more graph which are necessarily not important for this lecture, but maybe in the exam, from the exam point of view, you will encounter this type of graphs. The second is of y is equals to log x, which is like this. So if you want to just imagine this graph, you can imagine it like this. Say we have a value of y that is equals to, say, 1. So how it will we will get the value of 1. So it is given, it is 1, that is 10 to the power 0. So for y is equals to 1, x is equals to 0. Okay. So this is our x is equals to 0. Okay. So this is the thing. Now you can just imagine this, and you can draw this graph also, but for the exam point of view you should remember all this graph, because it is very typical to draw at that time. So these are the graph that we have. Now next graph we have is of 1 by x and 1 by x square. So if you take the positive value of y, then the graph looks almost similar. You can see that. So this is of y is equals to 1 by x square, that is a blue line, which is like this, but it is falling more quickly as compared to this red one, which is of y is equals to 1 by x. So this red one is of 1 by x. Now the main difference between these two is that since we are taking the square value, we are always getting a positive value of y. So whatever value we take of x doesn't matter, as long as it is a real number, we will get a positive number, that is a positive plot that will be above this 0 x 0 origin, and we will get a positive value of y. So these are the five graphs that you should remember. The first one was of the straight line, that is y is equals to mx plus c. The second one was of exponential graph, which is equals to y is equals to e to the power x. The third one was y is equals to log x, and the fourth one are these two graphs, which are y is equals to 1 by x and 1 by x square. So if you are not seeing any comparative study between these two, 1 by x and 1 by x square, you can say any of these as this 1 by x or 1 by x square, depending upon the inverse relation that is given in the equation. Now, keeping the things that are taught in mind, so that are taught in this graph section, you can use it in forming the equations and using it to form the graph that will be asked in the questions also. Now let us move to the first order of reaction, that is the zero order of reaction. So what is the zero order of reaction? Say it is the differential form. So the question arises here that why do we call it a differential form of zero order reaction? If you see the equation here, it is written as in terms of reactant. So say we have a reaction that is going from A to B, where A is the reactant here. So if you want to write the rate law, then it will be simply rate is equals to k a to the power 0, because it is zero order reaction, so it will be raised to the power 0. Now from the first starting of this lecture, I have told you this form also of this rate, which is given as in terms of reactant. If we write change in concentration of A divided by change in time, and with a negative sign so as to maintain the sign convention. We can also have a say 1 by n, that will be stoichiometric coefficient of this A, but since we are considering that that we are not having any coefficient or something like that, so we will just take the simple form, that is dA by dt with a negative sign. Now if you integrate this equation whole, then you will get the integral form. So this is the integral form of rate law, and this is the differential form of rate law. So the integral form of rate law is like this: A concentration of A at any time t is given as say we are starting from t is equals to 0 to t is equals to t seconds. Then in that case, the concentration which will be at t seconds is equals to the concentration that was at the initial time at t is equals to 0 minus kt. So k2 you know very well, so k is here the rate constant, and t is the time that has been passed through, or the time interval which we are considering for calculating the rate of reaction. So this was zero order of reaction. Now if you look at its derivation that I have given here, so what we have done here is say that we have taken this equation like this, that is dA by dt. Now we have placed the say variable on one side. So since dA a by a we will take here, sorry, this will be dA by a. Now since a is having a power of 0, we can just remove this as 1 and take it as 1. So it will be eventually dA is equals to k dt with a negative sign here. Now when we will move further, we will integrate it, that dA will be equals to, we know very well that integration of dx from say a to b will be x ab, then we'll put this values, that is final minus initial b minus a. So we have done the similar thing here. So we have written here that dA integration will be equals to a with a naught to at. Yes, also it will have a negative sign here also. Okay, so it will have a negative sign here. Now later on, when we will put this value, that is at minus a naught, so let me draw it for do it for you. So our starting equation was like this: dA by dt. So for first zero order, we have this value as raised to the power 0. So these are the starting equation in terms of reactant. Now if you take the variable on same side, this a to the power 0 can be written as 1, this k dt. Now we'll integrate it. So concentration will go from a naught to at, and time will go from t is equals to 0 to t is equals to t seconds. Now since this k or the rate constant is constant, it is in the name only, so we'll take it outside, and this dA will be given as a going from a naught to at is equals to, this will have a negative sign also, kt, which will go from 0 to t. This will be minus at minus a naught is equals to kt. Therefore, this equation can be eventually written as a naught minus at is equals to kt. So this is the final equation we do have here for the zero order reaction. Okay. Now if we look at the graph here, so how we'll compare this graph? So we know the equation, we have find the equation also. It is as at is equals to a naught minus kt here. So we have just rearranged those terms. Now if we compare it with the equation of the straight line, that is y is equals to mx plus c, so we have again arranged it again, that is y is equals to mx plus c. You can very clearly see here that m is equals to k, x is equals to t, and c is equals to this. Now children get confused that which term should be taken as mx, whether this one or this one. So if you find, so we are having an addition of these two, you can say, terms, but you have to find that term which has a constant value. So you can see very clearly here that this value is constant, so we will take this as c, and the remaining term, which is this one, we will take it as mx. Now we are plotting a graph of y against x, so y will be here 80, that is here, and x will be this t, that is time. So we are plotting a graph of change in concentration of A with respect to time. That is the final graph we have. Now this graph will have a negative slope because minus k is there, so it will have a negative slope, plus the intercept, that is the value of c, will be this one, which will be a naught. So if you are given a question, a graph, and said that it is a zero order reaction and the intercept is given like this, say some value is given a, and it is said that we are plotting a graph of concentration at a change with respect to time, then if you are told that yes, this is the intercept, that then the initial concentration will be equals to the intercept of this graph. Okay, and the slope, that is m, if it is mentioned, that will be the rate constant. We'll just take the negative sign, so rate constant will be equals to minus m. So I have written just the with again using the negative slope term, so we have just put that m as minus m, and then written the same equation as y is equals to minus mx plus c, which is the equation for this graph. So in this way you are using the graph thing. So that's why I mentioned it earlier about the graph. So you should be aware about the graphical methods. It is used in mathematics, physics, and chemistry as well, in the various chapters. Now again we have a graph here of rate against time. Okay, so we have a graph of rate against time. So it will be 80, sorry, it will be 80. So here we are changing the concentration of A and seeing that what is the effect on rate of reaction. So you know very well that for the zero order reaction, the rate law is written as R equals to K A naught. That A 0, that is, it is not affected any way by the concentration of A. So whether you change this concentration of A, sorry again, so it is the concentration of A. So whether you change the concentration of A by any amount, it will not change the rate of reaction and it will remain constant. So in this way you can explain this graph. So if you again compare it with y is equals to mx plus c, then you can see very clearly here that we do not have a constant, that is c. So c is equals to 0 here. That is, the equation become y is equals to mx, or y is equal to mx plus c also. You can write c also here, because as we have removed this a0, we are getting a k constant only. So y is equals to c, that means y is having a constant value always. Again, so this will be 80. So this is for the zero order reaction, that is rate versus concentration of A. Now let us move to the next order of reaction, that is the first order of reaction. So what is first order reaction? So first order reaction is said that R will be equals to K, that is the rate constant, multiplied by the reactant concentration raised to the power 1. Why? Because it should be 1, it is a first order reaction. And again we have used those rate of disappearance of A. In terms of that, we have written the rate law, that is minus dA by dt is equals to Ka. Further, if we integrate this equation, we will get this final equation. So let us see the derivation. So again here we have just arranged the terms, that is minus dA by dt. We have put the A here and moved the dt here. We have cross multiplied it. Now we know very well that 1 by A integration, if limits are not mentioned, then it will be equals to ln A plus C. And in case of in the limit is mentioned, say we have a limit, that is A and B dA, then it will be written as ln A, where this whole value will grow from A to B. So you must remember this integration very well to get the value. So why I am giving the derivation part here, because in some cases you must be given a different rate law and you will be said that okay, now find out the final differential form. So for that case I am giving you this derivation as well, so that you can get a grasp for it, or in the case you forgot the formula, you can quickly derive it. So it is possible if you are good with this calculus. So here is the thing that we have remaining is the that we put the value of a naught and a. Similarly for time we have from 0 to t. So if you put it here, it will be like this: ln a minus ln a naught, okay, it will be equal to kt. Then minus and minus will be give us this one, that is ln a naught by at is equals to kt. So this is our final rate law for the final integrated rate law for the first order, or you can again rearrange it and write it as ln a naught is equals to ln a plus kt. So from this property that ln a by b is equals to ln a minus ln b. If you are not aware about the properties of ln, so let me tell in short. So there are basically three properties that are used always in the chemistry, whether it is ionic equilibrium, whether it is equilibrium, or whether it is you say chemical kinetics. Only three major properties which are for ln and log both, you can say. So it is like this. So if ln a by b is given, then it can be written as ln a minus ln b. Second one is if ln ab is given, then it can be written as ln a plus ln b. Third one we have it is if say it is written that ln a, where a is raised to some power x, then it can be written as ln ax. So only this remembering these three you can say properties of ln, you can solve any question. And the fourth property that is you must be aware about it, that if something is given in exponential form, that is ln ex, or you can sorry ln x I'm saying log ex. So it is similar to ln a, which will be 2.303 log a. So this is the fourth, you can say fourth one you should remember. So if you remember all these four properties of ln, you can solve any question of related to logarithm, and plus those four to five graphs and some of the you can say minor differential laws, calculus laws, and you can use them all to solve overall the derivations. Now this was for the first order reaction. Now let us see the graphs of first order reaction. So this is the first graph we have here, that is of change in concentration of A with respect to time. Now if you see the equation here, it is written like this. Okay, so we can transform it later and write it as ln at by ln a naught. That will be equals to minus kt. Now if you take the anti-log here, sorry, ln a naught. Now if you take the anti-log here, it will be given as e to the power minus kt is equals to at. If you multiply it here, it will be a naught. So this is also a form of first order reaction. So this is one more property of this log, you can say. So if it is written that log a is equals to x, then a will be equals to 10 to the power x. And if log e a or ln a is written as x, then a can be written as e to the power x. So these are two more properties, and that's it, final for you. I will not increase it anymore. So if you just rearrange this and get this equation, you will get it at this one. Now I have told you earlier that we have two graphs of e to the power x. The first one was like this, and the second one was like this. Now if you remove this part, and since we are not taking a negative value of y, because what is y here, it is concentration, so concentration can never be negative. So if you remove this part and plus this part, because we are plotting graph of y to the power minus x, you will see that this is the only graph that we have here. So it is the same graph of this. Now the point here to mention is that this will never touch. So it will touch as t when t tends to infinity, then only this at will go to 0. Now the point that you can get from this graph here is that a first order reaction never completes. So it is never completed, and you can see from this graph also, and if you want you can see like this also. So you want this thing to be 0, that is it should be 0, and it is the graph. Now if you want to find this value of x, it is impossible. So whatever you take the smaller value, it will never tend to 0. It will only tends to 0 when x tends to infinity. So for this reason, this first order reaction never goes to completion. Or if for this reason it is minus, okay, no, it's a constant multiplied. So if we'll go here, you will get the same as 0 only. Okay, so for this reason, first order reaction never goes to completion. Yeah, the same thing written here. We are just comparing it with this y is equals to e to the power minus x, and you will get this graph. Now let us move to our next graph, which is as ln at to x. So it is of the first order only. So we take the initial form of this rate law, or an integrated form of initial integrated form of the rate law, which is as ln at is equals to minus kt plus ln a naught. So if you see here, we are changing concentration of at, so it will be y, and we are changing time, so this will be x. So you can see very clearly that this is a negative slope, so m is equals to minus k. That is why we are getting a negative slope here. So the children, the thing here I'm mentioning here mainly is that if we have a positive slope, it will be like this. It will be a negative slope, and it will be like this. And the intercept the same, that is ln a naught. So whatever with the value of this intercept will be the value of ln a naught. And suppose some value is given of this intercept, like say we have 2, then a naught will be equals to e to the power 2. So you should keep this thing in mind. So many times the graph is mentioned, the slope is mentioned, and you are set to find the rate constant, or so you can just find it easily. If you have this at and a naught, then you will put this k and you will find the rate constant. Now I've just written the equation that I've compared it with, that is y is this one, and this is this one. Okay, this x is time, and this C is ln A naught. So this is the these are the graph that we have. So we have one more graph here, that is rate against 8. So again here will be 80. So sorry for this confusion. So we will always plot a graph for rate is equals to 80. Okay. Now we know very well that this value is raised to 1 for first order reaction. Now if you compare it with this graph, you can see very clearly that we do not have any intercept. We do have a value of m, that is a positive value of k. So we do have a positive say slope plus this thing, but we do not have an intercept. In case if it has an intercept, then it will go like this parallel to this. Okay, but since we do not have any intercept, so intercept is equals to 0, so this value is equals to 0 and the graph moves downwards and passes through the origin. That is y is equals to mx graph. So students, in this way you can use your knowledge of graph of the mainly of the straight line, the secondly of the exponential, and in some case logarithmic and inverse graph, and you can easily determine the rate of reaction also. So you can be asked in the exam that say we have a graph which is given as rate against change in concentration of A, and it is given that it is going through the origin and having some slope that is greater than 0, then in that case we will say that the reaction is first order reaction. Now students, let us move to the most crucial part of this chapter, that is the half-life. Okay, so what is this half-life? So first of all, you should know very well what is half-life. So say we have a concentration that is equals to A naught, and we are told to calculate the half-life. So what here the half-life means that it is the time that is taken by the substance to go from A naught to A naught by 2. Okay, so this is the main idea of this half-life. So it is denoted by this T half, and it is the time required so that the concentration of reactant is decreased by half. Now if you find out the T half of the zero order reaction, it will be T half is equals to A naught by 2k. So if you want to derive, you can write it as like this. So we know that KT is equals to A naught minus AT. So now if you have to find the say T is equals to T half, then we are saying that this final concentration is equals to half of its initial concentration, that is A naught by 2. Further, this will be A naught minus A naught by 2, which will be A naught by 2. Therefore, T can be written as, so in this case it will be T half, because we are considered a concentration that is half of the initial. So T half will be equals to A naught by 2k. So in this way you can derive it also. So I will give you a general formula at the last that will be used and you can use it easily to find the half-life of any order reaction. Now next we have it of zero order reaction. So if you remember the zero order reaction equation, it was like this. That is equals to KT, which is A naught. Now we have said that we have to find the half-life, that is T is equals to T half, and AT is equals to A naught by 2. So it will be written as A naught by A naught by 2, which will be equals to KT. Now this A naught will get cancelled, and ln2 value is 0.693. If you put this K here, it will be this one. So this is the rate law for the means first order reaction half-life. Now if you look at both this half-life, you can see one thing, you can compare one thing, is that first of all that its half-life is dependent upon the initial concentration. That is, suppose we take different concentration of A naught, suppose we take 2, mole per liter, then we take 3 mole per liter, then accordingly this T half will change. But at the same time, if you look at the half life of this first order reaction, that is T half, whether you keep the value of A naught anything, it does not matter, it will only depend upon K, and you will get the same value of this T half. So that should be kept in mind, that for a zero order reaction, the T half is not dependent upon the initial concentration, while for a half first order reaction, the T half is sorry, for the zero order reaction, the this T half is dependent upon initial concentration, and the first order, the T half is independent from the from the initial concentration. Now, if we write a general formula, we can write it like this for any order. Now, the thing here to mention is that n should be not equals to 1. So you cannot apply this formula for n is equals to 1. Other than this, we can use it for any, say, any order reaction, given that one more condition we have here, that the reactant that we are using initially, so it should be only one reactant, so it should not have multiple reactants. So A should be going to B, that should be the reaction, or A should be going to B plus C. Means we are having a you can say monoreactant, that is A, and from that only the reactant is taking place. Then for that case, we can write the half life as this. Okay, you can see very clearly here this, that half life is proportional to 1 by n. Okay, so this was all about the half life. Now let us move to a gas phase reaction. So we will see how this rate order is applicable to gas phase also. So for gas phase reaction, we do not take the concentration much, you can say, we are just dependent upon its pressure. Now suppose we started a reaction such that it has 1 mole of A and a pressure of P naught. A is going to B plus C. Now after some time at equilibrium, not equilibrium, at some time T, say, the reaction proceeds and some of the moles of A goes to B. So due to this, the partial pressure of A will decrease, so it will be P naught minus P. Now since 1 mole is going to produce 1 mole of B and 1 mole of C, we will get a P ATM, that is reduced, equals to P ATM and P ATM. Okay, so this will get this, it is final. Now if it is a first order reaction, say, then we know very well that the rate law is given like this, that is K is equals to 2.303 by T log P naught by PA. Now if you further simplify this reaction, so we use the simplified form only for our numerical calculation. So it will be like this. So if you calculate the P total in terms of P total, if you calculate, so at time T, the P total will be equals to P minus P ATM plus P ATM plus P ATM. That is this. Now if we will then further, then you will get as P is equals to Pt minus P naught. Now we can see very clearly here that the pressure of A at time T is P naught minus P. So since we have got the value of P, we will put it here and we will get it as 2 P naught minus Pt. Okay, so we are representing this concentration of pressure of A in terms of total pressure. So this Pt here is total pressure. Now children, the thing here you should keep in mind is that this is not a general form. Okay, so this is not a general form at all, because in some cases you will see that the reaction is not having the same equation that we have used here. So maybe we can have a 2b or n plus 3c. Then in that case, this will also change correspondingly. Similarly, this has changed. Then it will be also 2p plus 3p. Okay, so this will also change. So 5 minus 4, 5 minus 1, that is be 4p. Now pt minus p naught. Okay, so this will be, say, divided by 4. Yes. Now it is p naught minus p, so it will be also divided by 4. Now this will be multiplied here, probably 4 p naught minus plus P naught, which will give us the final equation as 5 P naught minus Pt. Or this equation will be also transformed and it will be written as log P naught by 5 P naught minus Pt. So I'm making the point that is here is that you should remember this thing that it is not a generalized form. It is given in NCERT also I've seen. So if you have to see the equation, the balanced chemical equation, and accordingly you have to derive the final formula. Okay, so this should be kept in mind always. Now let us move to some questions. So we have seen enough theory for today. Now I will solve some questions for today. So we have a first question here. So it is a direct theoretical question which says that the rate constant for a zero order reaction is what? So it is asking for the rate constant of a zero order reaction. So you know it very well. We have derived it also. It is C naught minus Ct by T. So this is our answer. So I have to put up a you must be saying that why you put a easy question. So I put a easy question so that you can remember the formula, because in this chapter we have many formulas for each and every order of reaction. Same thing is done in the derivation form. So we have taken this, then we have integrated this thing, and then we got our final answer as K is equal to C naught minus Ct by T, where C naught is the initial concentration and Ct is the concentration at time T. Now let us move to a different question. It says that the rate constant for a zero order reaction is given as, so the value of K is given. Two into 10 to the power minus 2 mole per liter per second. If the concentration of the reactant after 25 seconds, so the time is 25 seconds, is 0.5 mole per liter, that is M. Now what is the initial concentration? So it is already said that is a zero order reaction. So we know the formula very well, which says that K is equals to Kt is equals to A naught minus AT. So we have this AT, we have T, we have K. If you put all this in this equation, then you can find this A naught. So the solution is given like this. So we know that this is the rate law. Accordingly, we will put this values and then we will find this x1. It is initial concentration and we will find it as 1.0 m. Okay. So in this way you can solve this question. So it is a direct numerical type question which in all values are given and you have to find your final answer. Further, we have a second question here. So it says that the time of a half-life period of a certain reaction that is going from A to the product is 1 hour. So T half is given. When the initial concentration of the reactant is, so initial concentration is 2.0 mole. How much time does it take for the concentration to come from this to this if it is a zero order reaction? So we are given that the reaction is a zero order reaction. That is, if you remember the formula for this half life, it is given as T half is equals to A naught by 2K. So in this case, we are set to find the concentration. So the time taken, that will be concentration will go from 0.5 to 0.25. So if you remember the formula again, so we will use that formula only, which is Kt is equals to A naught minus At. So we are given the initial and the final concentration and we have to calculate this time t. But for that reason, we know we have to calculate this value k. So which we will calculate using this half life information. So if you put this value here, that is 1 hour. Again, A naught is 2, then we have 2k, then k will be equals to 1. Okay, so you will find the value of k. Now we'll put this value of k in the zero order final integrated law and you will get an answer. So you can see the solution also. So for a zero order reaction we can write t half at like this. Now this value are given, so it will be 1. Now if you take this value of k that is equals to 1 and put it in the final integrated rate law of zero order reaction, then it will be 0.5 minus 0.25 by 1, that will be 0.25 hour. So this was the formulation of this question. Now let us take a different question here. So children, do not get confused. So this is only 99.9%. This does not mean anything. This to this thing. It is said that according to the question that for a first order reaction, the time required for 99.9% completion of the reaction is take place is dash of this half order. So we have to compare this say 99% completion to this half and this 1/4. Okay. So what is meant this by this T 99.9%? So first of all, you should get about the idea of this meaning. So it says that 99.9% of the reactant has been consumed. So what is the remaining say product? So reactant. So if it is 100%, then 99.9 that will be equals to 1.0.1%. So 0.1 percentage of this reactant is remaining. So if we take the initial concentration as 0, then the final concentration of the reactant will be 0.1. Now what else is said here? So it is a first order reaction. So if you take this equation, which is ln A naught by AT, and if you put these values, it will give you 100 that is initial by 0.1. You will get this value. Now what else is given? So we have to compare it with the T half. So T half, what is the value of T half? It is 0.693 by K. You can also solve this equation. So it will give you the 0. So ln 1000 will be equals to 2.303 multiplied by 3. This is 99.9. Now if you compare both these equations, so you can find out the value of K from here, which will be 2.303 multiplied by 3 by K, and it will be written as K is equals to 0.693 by K by T half. Sorry. Now you can equate this equation and this equation, and you can get the final relation between this T half and T 99.9%. So let us see the solution. So we have done the similar thing, but in one step, say. So we have taken 100 minus 99, that is 0.1. Okay, it is same. Then we have just put the values here. So we have taken this K as directly. So it is written directly that, okay, so it is T half in K in terms of T half ln 2 by at 1 to 1. Okay, so if you just use that also, you can solve this, and it is done in same order, just they have escaped one step. So we will get this value as 0.1 T. So this is as for 99.9%. Now what is the main thing that should be kept in mind here is that children often take the concentration at time t as 99.9, but it is not so. It is according to question. We are just saying that the concentration of the reactant is been that is been consumed is 99.9%. So the remaining reactant will be always 0.01%, 0.1%. That will be this one. So this is the main key point about this question. So that's why children makes mistake in this question, because they take 99.9% as the reactant concentration at time t. Now let us move to this question number 5. So it says that a first order reaction is half completed in 45 minutes. So it is very easy to say what is written. So it is given that suppose this is the half life of this. So if it is given that 0.693 by 45, so we get the value of k. How long does it take for 99.9% completion? So it is just the opposite of that previous question. Now do not get confused with this terminology. It is just the code that is not decoded. Okay. So T 99.9%, what does it requires? First of all, what sense of reaction is it? Is a first order reaction. That will be 100 by 0.1. So this will be our after putting the value, this we will get. And what is this k value? It is 0.693 by 45. So T 99.9% will be equals to 3 into 2.303 into 45 by 0.693. So if you solve this, you will get your answer. So I have done put up a solution also. So k is equals to this thing, and for say for we have this 99.9% completion, and we will get it as 7.5 hours. So we have say we have just change this 44.4448 minutes into hours. Okay, so this was for today's lecture. So we have solved 5 questions. Now I will show you 5 questions one by one and give you a little hint of it, and then you have to solve this question by yourself. Now the first question is that an organic compound undergoes first order decomposition. The time taken for its decomposition to 1 by 8 to 1 by 10 of its initial concentration are T1 by 8 and T1 by 10. So I put a difficult question for your say this practice, because it will make you more used to this chemical kinetics. Now what is the value of this T1 by 8 to T1 by 10? So the thing that is kept to be kept in mind about this question is that the final concentration is 1 by 8 of the initial concentration. Why? Because it is said that time taken for its decomposition 2. So this sentence should be well understood that okay, that the final concentration at time t is 1 by 8 of the initial concentration. Then similarly for for concentration to 1 by 10. So for both this is the T1 by 10 and T1 by 8. Now you have to find the value of T1 by 8 to T1 by 10 into 10. Okay, so you have to find this value. These are the 4 options. You can just put this thing and find the value of k, then just equate both these equations and get your answer. Now next question we have here is that it is of a gas phase reaction. Now children, keep in mind that when first you will get your say you will get your this integrated rate law in terms of a total pressure, and how I will do this. So say we have initial pressure of P naught. Now after time t it will be P naught minus P, this will be P, this will be P, and this will be P. So what will be the P total? It will be P naught minus P plus P plus P and plus P. So P total will be P naught plus 2P. Then you will just find this value of P naught minus P from here, and then you will use that the integrated rate law you will get in your final solve. So the key point here is that you should not use the general formula. You should define it the first using this chemical equation, and then you will get an answer. So let me show you the options. So this is the equation we have, and this is the information that is given. So it says that this temperature is not important, so not considering temperature. So half life is given of 14.5 minutes. Initially only dimethyl ether present as a pressure of 0.4. So initial pressure of this P naught is given. What is the total pressure of the system after 12 minutes? So you have the half life, you will find the value of K, then you will find your integrated rate law in terms of total pressure and P naught, and at final you will take the value of T as 12, you have the value of K, you have the P naught, put those value and get your answer. So these are the 4 options you have. Okay. So this is a tough question. During a nuclear explosion, one of the product is 90 SR with half life is equals to 28.1 year. So children, one point I missed here is that, so you should keep this always in your mind, that every nuclear reaction is a first order reaction. So any nuclear reaction we have is a first order reaction, until and unless it is not mentioned in the question that whether it is zero or second or any other order, you will take it by you can say default that it is a first order reaction. So this is a first order reaction, so you should keep in mind. So it is said that a half life is of this strontium is 28.1 year. Now, if 1 mu gram of this 90 Cr was absorbed in the bones of a newly born baby. Now it is said that okay, 1 a microgram of this strontium 90 is absorbed in the born baby of calcium. How much it will remain after 10 year and 60 year if it is not lost metabolically? So how will solve it? It is just an informative question, nothing is special about it. You will just have to find the value of k from this t half. Say we have this t half. So we know very well that if we have a value of t half, then you can find k, because in first order reaction it is not dependent upon initial concentration. So you will find the value of k here. Now I will take the value of t as 60 and as 10 and initial concentration as 1 milligram, or sorry, 1 microgram, and then you will find the this initial concentration, sorry, the final concentration at t is equals to 10 here and t equals to 60 here. So you will do it by yourself and get your final answer. Now let us move to the next question. So what does it says? It says that the half life of the reaction, that is this N2O5 2NO2 and half O2, is 24 hours. Starting with 10 gram of N2O5, how many grams of N2O5 will remain after a period of 96 hours? So this is the question we have here. Okay, the information that is missing is that, so I should mention it here. It is a first order reaction. Do not get confused. It is a first order reaction. We have this value of half life. You can find the value of k. Now it is said that initially it is starting with 10 gram of N2O5, and after 96 hours how many grams of N2O5 will be left. Okay, so you will do it by yourself. Now this is the last question we have for today. So it is also based on half-life. So I put up the many questions of half-life because children often get confused with this half-life concept. Now it says that half-life period for a first order reaction having an activation energy is itna and frequency constant is itna. Okay, so this is a different question. You cannot solve it because I am not taught this Arrhenius equation which says that k is equals to e to the power minus ea by rt. So those who know the formula, or those who don't know the formula can also solve it. So this is the only formula that we have at temperature say T. So we have this value of activation energy which is EA. We have this frequency constant which is A, and we have this half-life period for the first order reaction. So we have to find the half-life. So how we'll find it? Temperature is also given. We know the gas constant. So first to find the K using this formula, putting all the values. And whatever value you will get, you know the relation between this T half of first order reaction, that is 0.693 by K. That is 0.693 by A e to the power minus E by RT. So those who do not know the formula, I have written you for it, and I have mentioned the means specification that this is EA. So first convert this kilocalorie into this standard unit. This is the frequency factor, that is the value of A. So the answer should be in hour, so you should convert this hour also. This is the temperature, so it is in degree Celsius, convert it into Kelvin. Okay, so this was for today's lecture. So one topic I have missed from this differential integrated rate law. So I will just giving a glimpse of it. Tomorrow I will discuss this quickly because time is not allowing us to do so to complete this whole topic. So, the topic I have left it as pseudo first order reaction. pseudo first order reaction. So I'm just giving you the concept behind what is pseudo first order reaction. So I will explain you using an example. So say we are doing a hydrolysis reaction. Say we are doing it for glucose. Now, whenever you do the hydrolysis process, you take the water. So hydrolysis is mainly reaction with water. You can consider in simpler terms. You take this water concentration very excess amount. So you take the concentration of this water in excess amount. Now, when you do hydrolysis, okay, so this rate do depend upon this H2O to some extent. But since if you solve this rate law and all, and you use the experimental data and find the order of reaction, you will see that this water is almost negligible in the rate law. And why is it so? Because since you have taken an excess, so its small consumption also is not, you can say, reflected in the rate law. So pseudo means it is a kind of, you can say, that is imagination, that is not correct. Okay, so chalawa you can say. So it looks like a first order reaction, but actually it is a second order reaction. So we will properly mention this pseudo first order reaction in our next lecture, when we will see its rate law also. Okay, so for today just remember that it is a second order reaction that looks like a first order reaction due to the excess concentration of H2O, whose concentration change is negligible due to its excessive amount. Okay, so that was for today's lecture. Thank you. You can ask question if you have any.